In this video, we're going to look at the student's t-test, which is a statistical tool that you need to know about for A-level biology. And the reason that we need statistical tools in biology is that biology, like life, because it's the study of life, can be really messy. You're not going to get super clean data like you might get in some physics experiments. You need to be able to tell whether or not the results that you're getting, or when you're comparing one set of results to another, are they actually different, or is it possible that that difference is due to chance? And we're going to use the word statistically significant to mean things are unlikely to have happened by chance. Okay? So, for example, if you flip a coin 100 times and it comes up head 63 times and it comes up tail 37 times, does that tell you anything about the coin? Is it a fair coin? Is it a weighted coin? What you're really asking is, are the results statistically significant, or is that variation, 63 heads, 37 tails, is that just due to chance? Does that not actually tell you anything? There are a whole range of statistical tests that are used. For those of you studying A-level maths, you'll do some statistics, and if you study biology or any other science at university, it's a good idea to take some statistics courses just so that you're able to incorporate those into your papers and also have a better understanding when you're reading other people's scientific papers what the values mean. You'll often see P is equal to 0.05, things like that. We're going to look at the student's t-test. There's a couple of different t-tests. We're just going to stick to the one that's on the A-level biology spec. And this test is used to compare the mean of two different sets of data. So you might do an experiment where you collect data in one area versus another, or you're comparing two different species. You'll have two different means, and you're going to compare those to see if they are statistically significantly different. To use the student's t-test, the data must follow a normal distribution. If you look back at the previous lesson on variation, you'll see that we went through what a normal distribution is, what it means. You have a mean where most of the values are very close to the mean, and then it's symmetrical in terms of its shape around the mean. Remember, another name for a normal distribution is a bell curve. You'll sometimes see that, especially in popular culture or reporting in a newspaper. Your data set also needs to be large enough that your means are reliable. So if you only have a data set of 1, your mean is not going to be reliable at all. It wouldn't be appropriate to use the student's t-test. Importantly, the two sets do not have to have the same sample size. That's not as important for this as it is for other statistical tests. Let's take a look at the test. We're going to talk about null and alternate hypotheses first. Before you do any sort of statistics test, you should always propose a null hypothesis, and that's often written as HO. And a lot of students, when they see HO, HA, they get really freaked out. Very, very simple to make your alternate hypothesis and your null hypothesis. Your null hypothesis is always going to be that there is no significant difference between the two populations. So any difference in the means for the student's t-test would just be based on random chance. They don't actually mean anything. You are always testing your null hypothesis, and at the end of the student's t-test, when we've done the calculations, we'll look at how that's done. If you're rejecting the null hypothesis, then you are accepting your alternate hypothesis, which will be that there is a statistically significant difference between the two groups. So the difference that you see in the mean is not simply due to chance. And I've missed a bracket there. Let's have a look at the equation now. So t is equal to the mean of sample 1, take away the mean of sample 2, divided by the square root of the standard deviation squared of sample 1 divided by the number of samples in sample 1, plus the standard deviation squared of sample 2 divided by the number of samples in sample 2. So again, what do these mean? This is just the mean of sample 1. Remember, you're comparing the means of two different samples. So that would be the same, but for 2. This symbol, as we know from our lesson on standard deviation, means the standard deviation of sample 1. You'll see in some textbooks it's written as an S instead of the Greek symbol. And then last but not least, this will be the number. Wow, I cannot write. Number of data points in sample 1. And then these would be the same just for sample 2. Really importantly, before we go any further, you do not have to memorize this equation. You simply have to know how to use it. So if you get it on a test or an exam, they're going to give you the equation. They will also give you the t-table, which we'll look at shortly. So don't worry about memorizing those things. It's just a question of remembering what each of the symbols means and then how to do it. So we're going to look at the steps of doing the student's t-test, and this is the really long way, and I'll show you a shorter way in a few minutes. You're going to start by writing the null hypothesis. Then you're going to count your samples, so that's m, calculate your mean, x with the line over it, and your standard deviation for each group, so sample 1 and sample 2. You're going to subtract the mean of group 2 from group 1. Then you're going to calculate your standard deviation squared for group 1, divided by the number of data points in the sample. You're going to do the same for group 2. You're going to add those two together. Then you're going to square root it, divide the result of step 3, which is here. So divide this by the number that you got. And then you're going to get into your table where you have to calculate degrees of freedom, which sounds complicated, but is really, really simple. It's just n1 plus n2 take away 2. And that's going to help you figure out your row to look on your table. You're going to use a t-test value table to look up the critical value. You're always going to use, unless told otherwise, p is 0.05. That means that 95% of the time it wouldn't be due to chance. And then you're going to look and see, is your t value smaller than your critical value, or is your t value bigger than your critical value? If your t value is less than your critical value, then you are going to say the null hypothesis is accepted. If it is bigger than your critical value, you're going to say your null hypothesis is rejected. Let's have a look at an example of this. It looks much more complicated than it actually is. So let's have a look at an example together. We will do 2 examples together. Here's the first one. So is there a difference in biology test results between girl and boy students? You'll see we have the results from 10 girls, the results from 10 boys. The mean score of the girls was 72%, the mean score of the boys was 59%, and the standard deviation was 13.5 and 19.4 respectively. Before we do the actual t-test, it'd be worthwhile you actually having to think here and saying whether or not you think that there's a difference between the girl and boy scores. So looking at the mean score and then the standard deviation, without having done the statistical test, do you think that there's a significant difference between the scores of girls and boys in this sample? Okay, the first thing we're going to do is I'm just going to copy out all of the stuff from the question so that we have it handy. Then we need to write our null hypothesis. So our null hypothesis has to be there's no statistically significant difference between the boys and girls. Our alternate hypothesis would be there is a significant difference between the results of the girls and boys. Second one, count samples, calculate mean, standard deviation for each group. We've already done that. A lot of the time, if they give you a question like this, they will give you that data to begin with. And then we are going to subtract the mean of group 2 from group 1. So that is going to be x1 take away x2 means is equal to 72 take away 59, which is going to be 13. Then we need to do our standard deviation and dividing by the number of samples in group 1. So we'll start with group 1. I'll do that one in blue. We have standard deviation of 1 squared divided by n1 is going to be 13.5 squared divided by 10. which will be 18.225. We're going to do the same thing for population 2 or sample 2. And that is going to be 19.4 squared divided by 10, which is 37.636. Okay. Let's continue on another page. So just carrying on from before, the standard deviation squared of sample 1 divided by the number of terms in sample 1 was 18.225. Standard deviation squared of sample 2 divided by the number of terms in sample 2 is 37.636. So the square root of those two things together is going to be equal to the square root of 18.225 plus 37.636. We also already found that the mean of sample 1 take away the mean of sample 2 was 13. So if we look at the equation again, t was equal to sample 1, sample 2 means over square root of we have that, which is going to go there, and we have that, which is going to go there. So we end up with 13 divided by square root of 55.861, which is going to be equal to 1.739358081. That is our t-value. So we now have our t-value. We're going to have to do the final steps, which is looking up the critical value in a table. Let's look at how we do that. First thing we need to do is figure out the degrees of freedom. Degrees of freedom is really simple. It's n1 plus n2 take away 2. n1 was 10, n2 was 10, so my degrees of freedom is going to be 10 plus 10 take away 2, which is 18. That means that I need to look up in this row of my table for the critical value. We are always, unless the question asks us differently, going to use p is 0.05 as our default. So that is this column here, which means the value that we're looking for is 2.101. So our critical value is 2.101. Now all that we need to do is compare those two together, our t-test and our critical value. Our t-value was 1.739358081. Our critical value was 2.101. So our t-value is less than our critical value. So we have to accept the null hypothesis. So we accept the idea that there is no statistically significant difference between the test results of the boys and girls. Let's go and have a look at what those were again. So even though the mean score of the girls was 13% higher than the boys, because of the large standard deviations in both those scores, we cannot say that they're actually statistically significantly different. We can't say that in this class the girls are doing significantly better than the boys. And here by significant, we don't mean a lot. We mean in terms of statistics, something that isn't due just to random chance. How does that compare with what you thought at the beginning? Let's have a go at a second example here. This time we're going to test whether or not the leaf width in sample 1 is significantly smaller than the leaf width in sample 2. You can see we have 8 in each, and the mean widths, one of them, the first one is 38.9, the second one is 62.8, and then we also have our standard deviation. Have a go at doing this one on your own before I look through the answer with you. pause the video and have a go, and then I will catch you when you are finished. Okay, here is how I did it, rewritten everything out once again, just like before, and we will start with the mean of sample 1, take away the mean of sample 2, it's going to be 38.9, take away 62.8, which is going to be negative 23.9. We can actually ignore the negative sign here, it's not going to matter. We'll just write it as 23.9. And then we are going to do our standard deviation. If we add those two values together, we get 56.2525. Okay, let's assemble everything together then. What we end up with is 23.9 from before, divided by the square root of 56.2525, which is going to be equal to 3.186595854. Now, if you remember from the previous example, in the table, it's only going to 4 decimal places, so we can round this to 4 decimal places. Sorry, to 3 decimal places. So there is our t value. For our degrees of freedom, it's n1 plus n2 take away 2, which is 8 plus 8 take away 2, which is going to be 14. So we have our degrees of freedom, we have our t-test result. Let's look up on the table. So we're going to look at 0.5 and we're going to look up at 14. So the critical value is 2.145. Our t-test value was 3.187. 3.187 is bigger than 2.145. So we are going to reject the null hypothesis. There is a statistically significant difference in leaf width. Between the two samples. So in your assignment / homework for this lesson, I've given you your own student's t-test to have a go at. I've also included for you the tables, but you can always find them on the internet as well. Thank you. We are going to do Spearman's equation in the next video.